Okay, look at here at example 2 of buoyancy force. We have the average density of the human body is equal to 970 kilograms per cubic meter. Typical density of the seawater, imagine, is equal to 1015 kilograms per cubic meter. So we're just gonna determine what percentage of the body's volume is submerged. So that's like the one section. And for section B, imagine the average density of the human body after maximum inhalation of air changes from 970 changes to 945 kilograms per cubic meter. As a person floating in seawater inhales and exhales slowly, what percentage of his volume moves up, out of, and down into the water? Okay, so we're just going to see once breathing in and breathing out, what would happen based on this density. Imagine the density of the human body is going to be from 970, is going to change one inhalates, is going to just be lighter to 945, and once breathe out, it's just going to just get back to 970. So that's like the situation. We're just going to see the percentage of the body that going out of and into the water. And for section C, the question here, imagine if we are like in the Dead Sea, the saltwater lake in the Middle East is the saltiest large body of the water in the world. So, and if the average salt context is more than 6 times the typical seawater, this is like explanations. And the thing is that if someone's floating and swimming in the like that sea, 2/3 of the volume of the body of a person floating in the Dead Sea is observed to be submerged. Okay, with that assumption, okay, we're just going to need to just determine, the question is that determine the density in kilograms per cubic meter of the seawater in the Dead Sea. Okay, let's look at the example. And let's look at the starting from like the section 1. Okay, so based on the buoyancy force, we know that this formula, MB, is equal to rho W volume of the displaced water. Okay, MB is the mass of the body, rho W is the density of the water, and VW is the volume of the water displaced. Okay, and also we know that for the human body, we have the density formula. The mass of the body is equal to density of the body times the volume of the body. Okay, left hand side are equal, so we're just gonna equal the left hand side, and so the right hand side will be equal as well. Rho B VB is equal to rho W VW. Okay, and if you're just gonna rearrange this one, and the volume on the one side and rho on the other side, VW to VB is equal to rho B to rho W. So if you're just going to substitute here VW to VB, we know the density of the rho B and rho W is like the 970 is like the density of the body, and the rho of the water is like a 1015. And imagine if you're just going to say in the percentage, this ratio is equal to 95.6. So this is exactly the percentage of the body's volume which is submerged. Okay, so 95.6% of the body volume of the displays compared to like the volume of the body is submerged. So that's like a ratio. Let's look at the section B. If someone like inhalating and the human body changes to or decrease to 945 kilograms per cubic meter, we're just going to see what situation and the changes of this kind of like the submerged section in the water. So we're just going to use the same formula. So we know that like this relationship, and we know this relationship here. So we're just going to substitute for the second situation. So this like on the left hand side shows the ratio or the percentage of the volumes submerged in the water. And the right hand side, we know that like the ratio of the density of the body to the water, to the density of the water. If you just can substitute that one, the percentage of submerged of the body is like the 93.1%. If it's just going to compare with the previous section, the difference of these two figures, 95.6 minus 93.1% is equal to 2.5, which is the percent that is changing once that person inhalating and exhalating, or breathing in and breathing out. So that like a 2.5% of the body's volume will move as a result of like inhalating and exhalating. So look at the section C, the last section of this example. We have like the Dead Sea, which is located in the Middle East. We know that the assumption that the 2/3 of the volume of the body is floating in the Dead Sea is observed to be submerged. And the question here is to calculate the density of the seawater in the Dead Sea. So we're just going to use the same formula. So, but the only difference is that in this example, we know that the 2/3 of the volume of the body is observed to be submerged. So on the left-hand side, this ratio, volume of the water displaced to the volume of the body, we know that is equal to 2/3. So we're just going to substitute that one here. So if we just going to write here, the rho of the body to rho of the water that we're going to calculate is equal to 2/3, or 0.67. So this is like the ratio. So we're just going to solve this equation to calculate the raw water. So the raw water here is equal to, if we arrange this one, is equal to rho B divided by 0.67. And rho B, the density of the body, we know is like 970 divided by 0.67. And the result is 1,448 kilograms per cubic meter. You can see how big is, or how large is the density of the water is. I mean, compared to like 1,000 for the fresh water, which is like 1,000 kilograms per cubic meter, this is almost like the 50% more than the freshwater density. So this is the example 2 about the buoyancy.